Today we will continue our discussion and now related to the propagation of action potentials. We previously discussed the Nernst potential, here exemplified for potassium, that essentially states the membrane potential as a function of the concentration gradient across the semipermeable membrane. And this is written out for conditions at 37 degrees Celsius, and for typical potassium concentrations the membrane potential would be approximately minus 60 to minus 70 millivolts. We also discussed that if we have situations with more ions, so here illustrated for potassium, sodium and chloride, the resting membrane potential can be approximated by the Goldman-Hodgkin-Katz voltage equation shown here. And the beauty of biological excitable cells is that the permeabilities illustrated here for potassium, sodium and chloride can change very quickly, for instance in response to a voltage change with the membrane if we deal with voltage-gated channels, or interaction of a ligand with a receptor, which are the ligand-gated channels, typically present at postsynaptic neurons. So, a short recap of the action potential generation is shown here. This is a sodium channel, this is a potassium channel. Please note that the potassium channel is a persistent channel. It has basically one gate, while the voltage-gated channel has an activation and inactivation gate, which is why there are two little doors essentially here. And this is what happens during the generation of an action potential.
Its resting membrane potential. The activation gates of the voltage-gated sodium ion channels are closed and the inactivation gates are open. Voltage-gated potassium ion channels are closed. Depolarization is initiated by a stimulus which makes the membrane potential more positive, causing the voltage-gated sodium ion channels to start to open. As threshold is reached, many sodium channels open. Sodium ions diffuse across the membrane, causing depolarization. Voltage-gated potassium ion channels also begin to open, but more slowly. Therefore, depolarization occurs because more sodium ions diffuse into the cell than potassium ions diffuse out of it. As the membrane potential approaches maximum depolarization, the inactivation gates of the voltage-gated sodium ion channels begin to close, and the diffusion of sodium ions decreases. The potassium ion channels remain open, and potassium ions continue to diffuse out of the cell. The increased potassium ion permeability lasts slightly longer than the time required to bring the membrane potential back to its resting level. The extra efflux of potassium ions causes the membrane potential to become slightly more negative than the resting value. After the voltage-gated potassium ion channels close, the active transport of sodium and potassium ions reestablishes the resting membrane potential.
Please note two critical aspects in this video. First, there's no electroneutrality here, but these charges are assumed to be very close to the membrane and in fact are not part of the bulk solution, so they don't violate electroneutrality. Further, the potassium channel is not completely closed. It is slightly open, the permeability is finite. If that would not be the case, then we would not be able to generate a membrane potential initially. Please note that this door essentially is slightly open, and of the sodium channel it is essentially completely closed. So we have now a much better understanding how action potentials are generated, and a natural question, of course, now is how do they propagate? Because it's quite useless if you have a local generation of an action potential and it cannot be propagated, as propagation of action potentials is one of the essential functions of the neurons. So we're going to ask ourselves the question, assume that we have a local generation of the action potential, and how fast can these action potentials be propagated? And the first question is indeed, how far can they travel? And assume that we have a local generation of an action potential, and otherwise the axon is completely passive. So there are no other voltage-gated channels available in the axon. Then how far can it travel by passive conduction, which is also known as electrotonic conduction? And this is relevant, as we will see shortly. Now, to better understand that, we need to discuss the cable equation, which is an equation that describes this passive conduction of the action potential. Now, more details are in the book, but in short, this is a cartoon of a little part of an axon. So this is a cylinder, and the length is delta x, and we have indicated the 5 currents, which is a current on the left side that enters the axon, a current on the right side that leaves the axon, the possibility to apply an external current, i.e., and 2 other currents that essentially leave the axon towards the outer part, extracellular space, which is first the resistive current, IR, and the capacitive current, IC. And this is the corresponding electrical circuit of this little part of the membrane. So again, here our external current, this is the membrane resistance, the membrane capacitance, and the actual resistance. Of course, in reality, we have many of these circuits in parallel. So if you go into a little bit more detail, we can make the current balance according to Kirchhoff's equation. So the sum of all currents should be 0, or the capacitive current should equal these currents, and then we can write, using specific values of the, in this case, actual resistance, a little bit more in detail, the currents as a function of the dimensions of this axon. In particular, we introduce here the radius of the axon, the radius A, in the expression of the current that enters the axon here on the left side. More details are in the book. So we can do this for the current that enters the axon segment, the current that leaves the axon segment, and the external applied current and the resistive current, and the membrane current, resistive membrane current. So this is the full equation. It's also in the book, equation 3.3. So we have the membrane capacitance times the change in the voltage as a function of time, which is the capacitive current, and that equals this expression. More details once more are in the book, and you can simplify this to this equation 3.4. And then we can write a little bit more compact, introducing the membrane time constant, tau m, and the length constant, lambda. So this is essentially the cable equation, equation 3.8. Now, what exactly are these membrane time constant and length constant? Well, they are defined as such. The membrane time constant is the product of the membrane resistance and the membrane capacitance, and the length constant is defined as the square root of the ratio of the radius times the membrane resistance and the actual resistance. So this allows us to write the cable equation in this form. Now, to present a little bit more detail and to get a feel for the membrane time constant and the length constant, we can have a look at this figure again. At the top, again, our electrical equivalent circuit of the passive membrane, the membrane resistance in parallel with the membrane capacitance, the axial resistance, and the various currents we discussed. Now these two components, indicated in red, the membrane resistance and the axial resistance, are part of the length constant lambda, and these two, the parallel configuration of the membrane resistance and the membrane capacitance, are the product of those is defined as the membrane time constant, and they are very important for the action potential propagation in the electrotonic conduction of the action potentials, including the distance and the velocity, as we will show shortly. Now, to get a feel for the cable equation, it can be handy, it can assist to consider two extreme situations. And the first one is a steady state solution where we assume that the external current is constant. So we have a little cylinder, part of our axon, and we inject a particular current at a particular position, and we wait sufficiently long that there are no changes in the currents anymore. That means that there's no time, that the time derivative, the partial derivative of the voltage as a function of the time, so the time derivative is zero, and we are left with this part of the equation only. Repeated here for convenience. And if we do so, we wish to know the membrane voltage as a function of the distance. So this is our equation. Now this is quite easy to solve because outside the place of injection of the current, the external current is zero as well. So we are left with this equation, and the solution of this differential equation is given here. So the membrane voltage as a function of the position is a constant, V0 times the exponential of minus the distance over lambda. And how does that look like? Well, it looks like illustrated here on the left and on the right. We have our current injection. We wait sufficiently long for a steady state, and then current will leave the axon in both directions, where the current density will decrease as a function of the distance, and that of course defines the membrane voltage. And this is a sketch of how the membrane voltage drops as a function of the distance from the site of the injection. Now this is very similar to an action potential being generated here. And this is once more illustrated here. It's a little bit redundant to the illustration on the left. Local current injection, and if we measure at different positions farther and farther away from this place where the current is injected, we will find that the membrane voltage will drop, and as is described by this equation. Now it's clearly, it's directly obvious that the longer the lambda is, so the larger the length constant, the slower the membrane voltage will drop as a function of the distance. So the length constant is an important part of how fast membrane voltage that is located at a particular position drops as a function of the distance. Now another solution of the cable equation is to consider a spatially uniform voltage. So we remove the spatial derivative essentially. If we do so, then we have this equation, and that is also quite easy to solve, and this is the solution. So the membrane voltage as a function of time is a constant times 1 minus an exponential function to the power of minus t over the membrane of the membrane time constant. And this is how that looks like. So now we apply a uniform current across the axon, so there's no spatial derivative, and we do it as a current pulse. So we start the current, it's kept on for a particular duration, and then we turn it off again. Now in that situation, the membrane will essentially charge up to a certain value, depending on the amplitude of the current pulse and the duration. And when the current is turned off, it will discharge. And both are described by exponential function as indicated in the graph below. So our lambda on the left, once more defined by this equation, is essentially a measure for how far an action potential can travel with relative preservation of its shape. And the membrane time constant, which is the product of the membrane resistance and the membrane capacitance, defines how fast the local membrane potential will change if local current is injected or a particular potential is applied. And so with this knowledge, we will come back to our initial question: how far can action potentials travel by electrotonic conduction only? Which is why we started out with. Well, now we can give a more precise answer to this question, because it depends on the space or membrane length constant. Those two names are used for the same thing. So the membrane length constant is also known as the space constant. So that it depends on how large that value is, how far an action potential can travel by electrotonic conduction only, because at a position lambda from the position where the action potential was generated, so if you move away a distance lambda, then the action potential has decreased to 1 over E of its initial value, which is typically for axons between 0.3 and 10 millimeters. So is this passive conduction, the electrotonic conduction, then sufficient for action potential transport? Well, we do know that we have axons that need to transport action potentials over a distance of several centimeters, sometimes even up to 1 meter. And if the lambda is of the order of millimeters, then it will not be sufficient to transport the action potential over that distance, because then eventually action potential's amplitude will have dropped to 0. That essentially happens after 3 to 5 lambdas. So what can we do about it? Well, you can make very short axons. So a very short axon, a synapse, another short axon, synapses. That is a way to do it. But it has disadvantages, amongst others, that you need a lot of synapses. And they slow down the transport, as we know, and they use a lot of energy. So there are two reasons not to do that, while that will not work. You can also increase the lambda, make it even larger, and that is indeed one of the things that nature does, as we will see in a moment. And the third option is to create a new action potential, so to boost it. So the action potential drops to a particular value, and when it's getting close to being too small, then we generate a new action potential. And this actually is what nature does. So it both increases lambda and it creates new action potentials. So how can we increase lambda? Well, that actually is it directly follows from the equation. You can, for instance, increase the radius of the axon, or you can increase the membrane resistance, or you can decrease the axon resistance, the axial resistance. And this is a worked out example for two axons with different diameters, assuming a similar membrane resistance, specific membrane resistance of 2000 ohm per square centimeter. And this is for the squid axon that also has a slightly smaller specific axial resistance than a mammalian axon. And for the squid axon, we find a lambda of 18 millimeters, while for this particular mammalian axon with a thickness of only 1 micrometer, or a radius of 1 micrometer, the lambda is 0.3 millimeters. So it helps if you make the axons thicker, larger, but clearly, of course, there are space constraints in doing that as well. You can't make them infinitely large. Another option is to increase the membrane resistance, and this is not an axon clearly, this is an electrical conductor. This is the core, which could be copper, and this is insulation. And this very much looks like myelinated axons. So what are those? Well, myelin is a way to increase the membrane resistance. And so Rm, because it is essentially a non-conducting substance. And we do know we have a lot of myelinated axons in our body. So myelin essentially increases the membrane resistance, and that increases lambda. Now this is the expression for an unmyelinated axon, and for a myelinated axon the expression becomes slightly different. This is a square root sign, it's not completely visible. In the book you can read why this indeed is the expression for a myelinated fiber with the different dimensions included, in particular the square of the naked axon, of the radius of the axon itself, and A2, the radius of the axon with the myelin. Once more details can be found in the book. Now, the other option was to make new action potentials with boosters, and those are essentially the voltage-gated ion channels. So another movie to illustrate that.
An action potential, depicted as a red band, is propagated in one direction along the axon. During an action potential, the inside of the cell membrane becomes positive with respect to the outside. An action potential generates local currents that tend to depolarize the membrane immediately adjacent to the action potential. When depolarization caused by the local currents reaches threshold, a new action potential is produced adjacent to the original one. Action potential propagation occurs in one direction because the recently depolarized area of the membrane is in absolute refractory period and cannot generate an action potential.
So while not shown in the cartoon, but this assumes that there are many voltage-gated channels very close to one another that are subsequently activated by the membrane depolarization. Now, because of the myelin and myelinated axons, those voltage-gated channels are separated by a particular distance, which is essentially the length of the myelin sheath. And the location where the voltage-gated channels are mainly located are known as the node of Ranvier's. So those are the spaces in between the chunks of myelin where essentially the action potential boosters are located. So what happens in practice, here an action potential is generated, which is an active process. Then there is electrotonic conduction along the myelin. So there's a small drop typically in the action potential amplitude, but it is still large enough to induce a membrane depolarization sufficiently large to activate the voltage-gated channels, the voltage-gated sodium channels, to generate a new action potential, which is illustrated here. So we have a new action potential here, and then there's passive conduction, active process generating a new action potential, and again passive conduction. And this is known as saltatory conduction, because if you would look from a distance, it is like this action potential sort of jumps from node to node, which of course is not the case. It's generated here, and a little later, another new action potential is generated here. So this is called saltatory conduction. And this is different in an unmyelinated nerve, where essentially the voltage-gated channels are spaced much closer to one another because the electrotonic conduction distance is much smaller. So in sum, we discussed shortly the cable equation. We introduced the concepts length constant and the membrane time constant. You do understand the effect of axon diameter on the length constant, and you also understand why myelin has an effect on the length constant and increases its value.